Okay, so here we're looking at total running time. So I'm no longer going to talk about sort of that these could be constant amount of time, or for example like a linear amount of time. That's not what we're doing on this set of slides. We're going to look at sort of exact running times. So how many operations are done here on the first line? Well, let's say the dot is one operation, so that's 2, 1, 2. We have 3 here, and let's say the creation. So that's us creating an array. Let's say that has a constant cost as well. So 4 computations on the first line, and we have 3 on the second line. Okay, so unlike when we did this for insertion sort, I'm not going to break this into the cost of the line multiplied by the number of executions, or sorry, 2 columns where I have cost and then another column for number of executions. We're going to put those together. So we'll say, what is the cost of this? That'll be 2, and we're going to compute that by the number of times it executes. So I'm going to say that's m plus 1 times. Alright, I'm going to use a different variable here called m instead of n. So I'm going to use m instead of n because this is our merge function. And I want to differentiate between m and n. So from here on out, I'll use n to denote sort of the total number of elements in the array, and m to denote the number of elements passed into merge. So if I go back to this tree here, you'll see that sometimes when I'm merging in 3 elements here, so m is equal to 3, and over here m is equal to 4. But n for us in this example is always going to be equal to 7. So I'm just going to do a different variable name just to differentiate between the two, and that'll be helpful later on. Alright, so that's the only thing special about that. And why is it m plus 1? Well, because k goes from 0 up to m, the total number of elements passed into here, so the size of out. But we have to know when we've sort of gone one past. So this will say when k is equal to out.length, which means we've done 0, 1, 2, all the way up to m. And since we've got the base 0 there, we have an m plus 1 here. Okay, so 2 times m plus 1. 1, 2 times the number of times that loop condition is checked, which is m plus 1. Alright, how about this line? How many computations are done here? Well, we have 1, 2, 3. And how many times does that line execute? Well, the body of a loop always executes 1 fewer time than the loop condition, so we'll have 3 times m. Here's where things get a little bit trickier. So how many times does this execute? How many times does this execute? Well, that will sort of depend on the number of times this condition is true. This is where things get a little tricky, and just like that, the number of times these lines execute depends on the number of times that those lines are false. But we do know one thing for sure. We know that either this line or this line, one of those two will always execute. And same for this, either this one or this one. One of those will always execute. So for now, let me just denote that as, well, that's 3 times m. So 1, 2, 3. And this one's 2 times m. 1, 2. And I can basically just ignore this block down here. And the else is going to be 0. It's basically just a label. If you remember back to any time you've seen assembly code, your else, it's not an actual command that's run. It's just a label where you jump to in code. So I've got this in orange, and basically we'll say that these don't happen. That's one way to do it. Another way, if you want to be a little more precise, is you could say that this is 3 times, this right here would be like saying 3 times the length, and likewise this is 2 times 1 dot length. This is 3 times 2 dot length. Sorry, 3 times 2 dot length, and this is 2 times 2 dot length. But what do we know about 3 times 1 dot length plus 3 times 2 dot length? That's the same thing as just saying 3 times m, because m is going to be 1 dot length plus 2 dot length. Maybe it makes sense to inside here put m is equal to 1 dot length plus 2 dot length. Maybe that's an adjustment I'll make in my slides. Alright, well, if you add this all up, plus the 2m down here. So you add all of those up, what you'll end up with is that the time for merge is equal to 12m plus 9. Alright, well, I'd like to simplify that a little bit, because carrying around 12m plus 9, we're going to eventually multiply this by some other expression. I'm just going to jump ahead a little bit, and I'm going to say that we don't need the exactly correct running time of merge. We just want something that's close enough, but is also easy for us to use algebraically. And I'm a computer scientist. I'm kind of lazy when it comes to math, so let's make this a little bit easier to use. Where we're heading is to asymptotic complexity, and eventually to do asymptotic complexity, we'll remove lower order terms anyway. So let's simplify our expression. This is what we had. T of merge was equal to 12m plus 9. Well, I could pretty easily say this. T of merge is less than or equal to 12m plus 9. That doesn't really change much, except for I've just given myself an upper bound on it instead of saying it's exactly correct. It's less precise, but now it means that I can make this side bigger, and I don't sort of affect this inequality. So for example, I could say plus, I don't know, 67. Okay, sure, this is going to be bigger than this because we know this left side is exactly 12m plus 9. But instead of doing that, sorry, I should have put this m in later. But instead of doing that, I'm just going to make this other side bigger by multiplying the 9 times the m. And when I do that, I can add them together, and I've got T of the time to merge is less than or equal to 21m. Alright, so that's the cost of an individual call to merge. It's less than this. This 21m, again, is just going to be easier algebraically later on. So that's just the time for merge. What else do we need to know to calculate the total time of merge sort? Well, we need to know how many times do we call merge, and what's the value of m each time we call merge.